SwayamPrabha. Digital India. Educated India.
Hello, in this video we will discuss about beams. So, we will show you the viscoelastic solutions for beams under various loads. So, we will start with a brief review of the correspondence principle, where we showed we can get a viscoelastic solution by following these 4 steps. First, we need to identify the elastic solution. Once the elastic solution is identified, in that solution we identify the variables and replace it with Laplace transforms. So, for example, for strain we will replace it with epsilon s. Similarly, we will also identify the elastic constants and replace them by s times the Laplace transform. So, for example, here is the modulus E, we will replace it with E times E of s. Here I am only showing strain for variables. Of course, there are other variables like the stress, load, deflections, and for the elastic constant we know the other constants are like the Poisson ratio, bulk modulus, shear modulus, like that. Finally, we take the solution in the Laplace domain and inverse it to take it back to the time domain. Once we do the inverse Laplace transform, we get the viscoelastic solution to the problem. So, the last step is the inverse Laplace transform. Now, let us look how we apply this correspondence principle to solving beams. So, here we will start with pure bending. Here is the undeformed beam at the top and to the bottom is the deformed configuration of the same beam. Let us first define the coordinates. Let us say the horizontal axis is the x, which is starting here, and the deflection is in y, which is positive, is going downwards. So, let us say we represent the cross section of this here, y axis will be going downwards and the third axis is the z. Okay. So, let us say this is a beam is of length L. It is made up of a material with elasticity E. Currently, as a first step we will look at the elastic solution, that is why I said E, but of course, for the viscoelastic we will go with elastic relaxation modulus later. Okay. So, we say that we are applying a moment m about the z axis, and let us assume that it is a function of time, meaning with time the moment changes. The same moment is applied on both ends mz of t. So, let us say I is the moment of inertia about the z axis and y is the distance from the neutral axis. So, let us say we are talking about any point here, this distance is y. And sigma is the bending stresses, because once we bend a beam we have the bending stresses. For example, in this scenario we have stresses here as compression at the top and at the bottom as tension, and delta is the displacement. So, from the deformed to the undeformed, let us say this is the undeformed configuration. If we are focusing on the top end of the beam at the midpoint, this distance is the deflection we are talking about, delta. So, now let us look at how do we write the bending stresses in the beam. So, from solid mechanics course we know we write this expression that m by I is equal to sigma y is equals to E by R. So, we will use this expression to write what are the bending stresses. The bending stresses, let us say, is sigma is simply m, which is a function of t times y by I. And how do we get the deflection? We get the deflection from r because we replace it with curvature, which is again written in terms of the double derivative of the deflection. So, here is the expression for the deflection written in terms of m, e and I. So, previously we have seen that we would like to take all elastic constants in the numerator, but not in the denominator. So, we will rewrite this as moment by I times d, where d is the compliance. Okay. So, this we will call it as step 1, where these are the elastic solutions for the problem. We have found the elastic solutions for the bending stress sigma and the deflection in terms of the second derivative. Okay. So, first let us focus on the bending stress and try to solve this following the correspondence principle. So, what are the second and third steps? Steps 2 and 3, we need to replace the variables and the elastic constant. So, we will replace the sigma with the Laplace, and moment we said is a function of time. So, we will replace that with the corresponding Laplace transform. Y is the distance from the neutral axis, for the moment it is just a constant. I is the moment of inertia, which is again a constant. So, after writing these steps 2 and 3, what is the last step? Step 4. We need to apply the inverse Laplace transform. So, inverse Laplace transform for the stresses will be sigma of t, and to the right hand side we only have one Laplace terms, which is m of s. So, the inverse Laplace transform for that will be m of t. Okay. So, if we notice, we will see the elastic solution in step 1 is exactly the same as the elastic solution in step 4. So, we have seen this earlier for bars as well, saying that your elastic solution and viscoelastic solution are same when the equation does not have any elastic constants. So, for example, the bending stress here is only dependent on moment y and I, there is no elastic constants like E or Poisson's ratio. For that reason, we have the solution again similar to the elastic solution. But now let us look at deflection, because in deflection we see that there is one elastic constant, which is d, d is the compliance. So, now let us apply these steps 2 and 3 for the deflection equation. So, we will replace, we will simply write this double derivative and replace delta, which is a function of time, now in the Laplace domain delta of s. So, m of t we will write it as m of s, because it is only a variable, by I is a constant, and d we will replace it with s times d of s. Because d is an elastic constant, we said according to step 3 we should replace with s times the Laplace transform of the elastic constant. So, with this we will go into the last step, which is the inverse Laplace transform. To the left hand side it is straightforward, because there is only one Laplace variable. So, it will simply give delta of t is, to the right hand side now we see it in the form of s times product of two Laplace functions. We identify from convolution integrals that this can be written in terms of an integral of first derivative of a function times the another function. So, integral 0 to t d of t minus u and d by dt of m of t. times, okay, times d by du of m of u. Now, the moment is written in terms of the temporary time variable u, and this is multiplied with du. Okay. So, this will be the final solution for finding the deflection in the time domain. But one can also use this formula to find the deflection in the Laplace domain, because depending on the problem we are solving, sometimes it is easier to solve in the Laplace, which means substitute the compliance d and the load moment m in the Laplace domain and solve it, or one can directly use the last formula, which is the time domain formula, and directly substitute into the integral. So, with an example we will see, we will follow both these approaches and show that both approaches can be followed for easy loads, but one has to take a call depending on the kind of load one has to solve for. Just a small correction here, we forgot to bring this I in the denominator. So, let us add that here to correct the final formula. Okay. Now, let us try with an example and apply these formulas and see how we can solve beams. So, in this example we will take the given moment as m naught times h of t. H of t is the step function, meaning that we apply a moment at time t equal to 0 and then that is remaining as constant. So, we are simply saying that this is m naught times h of t. So, in the previous slide we have shown you the formulas to be used to find the deflection, but even there for the deflection there are two formulas. Either we can stop at step 3, which is in the Laplace domain, there we got it as okay. So, this is the deflection in the transform domain, which we have showed in the previous slide. Now, let us apply the loading. So, once see the loading and see that the loading in the transform domain m of s is simply m naught by s, because the Laplace of a step function is simply 1 by s. So, let us substitute that here. So, both these has cancel out, and then what we are left with is m naught by I times d of s. These are in the Laplace domain. So, finally, once we apply the last step and do the inverse Laplace transform, this will go back to the time domain, delta of t m naught by I times d of t. Okay. Now, let us derive the formula by applying directly the time domain integration formula that we have seen in the previous slide. So, in the previous slide we showed that in the time domain it is given by this integral 0 to t 1 by I times d of t minus u times d by du of m of u times d. So, in this we need to find what is dm by du. So, first let us write the given moment in terms of u, which is m naught times h of u, and the derivative of this is, since the derivative of the step function is the Dirac delta function, we will write it as m naught times the Dirac delta function delta times as a function of u. Okay. So, let us substitute this into the integration. So, let us bring this 1 by I out of the integral. So, d of t minus u times m naught as well, we can take it out of the integral because it is a constant, then what is left out is this Dirac delta function. Now, noticing that we have the shifting property of the Dirac delta function, this can be rewritten as simply d of t. So, we got the second derivative of the deflection delta of t is given as m naught by I times d of t, the compliance. So, we see with both the formulas we ended up with the same solution. Here we have not yet defined what is the mechanical model, meaning it could be a Kelvin model, it could be a Maxwell model or any other model, but once we know that, then we can substitute d of t to get the equation for the deflection in the beam. Now, let us look at another example where we have loadings occurring on the beam. So, let us see. So, here we see a beam which is supported at both ends, and let us take the loading as UDL, uniformly distributed load. Let us say this load is given as Q of t, which is Q naught times the step function h of t. Okay. So, and let us also take that the length of the beam is L. So, the total load applied is Q naught times L. Since we have two supports at either end, those reactions will be QL by 2. Q naught L by 2, Q naught L by 2. But from standard textbooks, we should be able to write out what is the expression for deflection of this beam at the mid span, or the maximum deflection of this beam which will be at the mid span. So, that is given as So, again we see that we have an elastic constant E in the denominator. So, let us write it in a such a way that we have the elastic constant in the numerator by replacing it with D, the compliance. So, we solve this using the Laplace formula for deflection, which is delta bar is 5 by 384, replacing Q of t with Q of s, and d with s times d of s. We also need to replace what is Q of s. Since we know that Q of t is Q naught times h of t, the Laplace transform of this is Q naught by s, because the Laplace transform of the step function is simply 1 by s. So, once you substitute that, this should simplify as 5 by 384 L4 by I, QS I will replace by Q naught by S times S d of s. Cancelling out both these s, what we are left out is 5 by 384 times L power 4 by I q naught times d of s. Okay. Now we notice that we only have to the left only one Laplace transform quantity, and to the right also we have one Laplace transform quantity. So, finally writing the inverse Laplace transform will be easy. Delta of t is 5 by 384 L power 4 by I q naught in d of t. So, this will be the final expression for the viscoelastic deflection which changes with time. Here we see that it changes proportional to the compliance d. So, now it depends on what is the mechanical model we choose. So, now let us say if we choose Maxwell model to start with. So, if we choose Maxwell, we have already shown that the compliance d of t is given as T by mu viscosity plus 1 by E. So, once I substitute this into the deflection formula, we should get delta of T as similarly as well I can change the mechanical model from Maxwell to Kelvin. So, let us see how the deflection changes for a Kelvin model. So, here again we have shown previously the compliance is given as here tau is the relaxation time or the retardation time here. So, once I replace this into this formula we derived, then the deflection of this beam at midpoint is so what we have seen in this slide is given the beam which is loaded with a uniformly distributed load, and this is a function of time because we are applying a step function, meaning at time t equal to 0 this UDL is applied and after that this is remained as constant. So, first we found the step 1. So, from any standard book on strength of materials or solid mechanics, we should be able to find this formula for maximum deflection in this beam which happens at the mid span. So, once we have this, then we simply went with the correspondence principle. We have replaced both the variables and the elastic constants and finally done the inverse Laplace transform to get the solution in time domain. And finally, we said since the solution has this d of t, now depending on which mechanical model we choose, the final expression for the deflection will change. We have shown it only for Maxwell and Kelvin, but as well one can extend it to any other mechanical model or even simply an experimental data. Let us summarize what we have discussed in this video. We started with a small review of this correspondence principle and then applied this correspondence principle to solve beam problems. We started with a pure bending and later we also have seen beam bending with loads as well. So, here I need to stress on few things about the applicability of this correspondence principle. So, we are able to apply this correspondence principle when the load, let us say P of t, can be written as let us say it is a spatial as well as temporal function, which means the spatials can be separated as g of x and the time functions are written as f of t. So, if we are able to separate out the spatial and the time loadings, then we can apply these correspondence principle. But let us say if both of them cannot be separated as two different functions, then these correspondence principles cannot be applied. That is the first comment I want to make. The second comment I want to make is what we have discussed till now is only for one dimensional problems. But the same approach can be extended also to 2D or 3 dimensional problems. So, we are not going into these 2 dimensional and 3 dimensional problems because of the limitations of the time, but those who are interested can look into that literature. The reason being, once let us say you are using a commercial FE package to do the viscoelastic analysis, the background is mostly from this 2D and 3D viscoelastic analysis. So, with this we conclude the week 4 material. From the next video onwards we will move on to the next week, where we will talk more about the characterization of these polymers and conclude by discussing about the design of polymers.